All right, ladies and gentlemen, we are going to start today with our discussion of nomenclature. So you will actually start writing formulas and naming compounds, and I can't stress enough how important that this is, because if you cannot name compounds correctly, then we're going to have problems. Okay, we're going to have problems. What do I mean by that? Well, you might not seem like it's a big deal, but if we have Na, boy, we got this board going again here. Should I have to do this every time? I wouldn't think. But I guess, let's say we got NaCl and you happen to name it Na2Cl. Would that make a difference? Absolutely. Now, sodium chloride is an easy one, okay? But we're going to run into a lot of different things, a lot of different stuff, you know? You're going to have to make sure that you pay attention, because is nitrate the same as nitrite? No. One letter difference, okay? So, this nomenclature is a very important part of your chemistry journey, because if you can't name it right, you're going to have some problems. So we're going to start out by talking about chemical names and formulas. Chemical names and formulas. The significance of a chemical formula. Now, as we talk about this, a chemical formula indicates the number of atoms of each kind of element in a chemical compound. Now, right here, when I show you a molecular compound, that should tell you some things. What does a molecule tell you? Huh? It is covalently bonded. So I should be thinking that I'm going to be dealing with what types of elements? Nonmetals. Okay? A molecular compound is going to be dealing with nonmetals, covalent bonding. So when I hit the next part of the slide, we're going to see a hydrocarbon. Carbon with hydrogen. And for this particular hydrocarbon, I have 8 carbon atoms, and I have 18 hydrogen atoms. Now stop and think back. Could you create this with your molecule kit? Could you? Yeah, should be able to. Okay? You should be able to take 8 carbons and 18 hydrogens and show me how this particular element would bond together. We know it's covalent bonded. We know it's a hydrocarbon. We could do that. Now, just like when we talked about molecules, we can also do the same with the formula unit. Remember, a formula unit will tell you that you have ionic bonding. So you're thinking a metal and a nonmetal could possibly be polyatomic ions. Okay, could possibly be polyatomic ions, and we know that when we're talking about metals and nonmetals, we're talking about cations and anions, and we're dealing with charges, mutual attractions between opposite charges. So the positive cations are attracted, the negative anions are attracted to each other. So if I have this particular formula unit here, aluminum sulfate. Now, the SO4 is a polyatomic ion. So if I look at this, I'm seeing that I have two aluminums. We always write as a subscript following the atom. So I have two atoms of aluminum. If I just look at the sulfate ion, the sulfate ion consists of one sulfur and four oxygens. So, based on the charges of aluminum and sulfate, I need different amounts of them. So that's why I have this parentheses with the 3. So, as I am distributing out, okay, as I am distributing that out, the subscript 3 refers to that entire unit that is involved there. So if I am looking at these, I see that sulfur, nothing behind sulfur signifies that there is 1. What's 1 times 3? 3. So in this particular formula unit, I have 3 atoms of sulfur. How many atoms of oxygen would I have? 12. So it's kind of like distributing out in math when you have the parentheses also. It's kind of similar to that. It's just the numbers are in different places. So those subscripts are just in a little different spaces. Now, I want you to notice, okay, like we talked before, we do not put 1s. You should never put a 1 when you are signifying a subscript, because that is understood. If nothing is next to the atom, it's understood that it's a 1. So as we go back through and just double checking, how many atoms of aluminum? 2. How many atoms of sulfur? 3. How many atoms of oxygen? 12. Okay, 12. Now, I am going to now pass out an ion sheet to you. So you have your very own ion sheet, and as I said, it's going to be important that you know where these are at in your binder, because you are going to use these throughout the rest of the year here in chemistry. You're going to understand that a lot of these things you will end up storing in your mind. You will use those so much that you don't need to look on your ion sheet. You're going to know that aluminum is a 3+. You don't need to look on your ion sheet. You know that any of the halogens are 1-. So these things are going to become embedded in your minds, but they are not there yet, so we have to use the sheet as a resource. So when we talk about naming monoatomic ions, now we are talking, let's break down. Monoatomic, what's mono? 1, okay? So we're talking about 1 atom here, all right? So, monoatomic cations are identified as simply the name of the element. So a cation, is a positive ion. Usually when we're talking about cations, we're talking about metals, because metals are the ones that want to give up electrons. We go back to the bonding stuff. Look at the alkali metals, group 1. They have one valence electron. They want to get rid of that one valence electron, so they have a full outermost shell. So you're going to see that the charge of the alkali metals are going to be +1, a cation. Lithium is the example we have here. Lithium +1, so when I see that lithium ion, that's exactly what I call it, the lithium ion. It's a little bit different for for anions. Okay? Anions are the negative ions. They are gaining electrons. What type of elements want to gain electrons? Huh? Halogens, and those are called what? Generalization is a nonmetal. The nonmetals want to gain electrons. So all of the halogens want to gain how many electrons? 1 electron. So what do you think their charge is going to be? -1. Look at the next row. The oxygen family. How far are they away from completing their shell? 2. So how many electrons do they want to gain? 2. So what is their charge going to be? 2 minus. 2 minus. All right? Now, when we talk about those anions, all right, when we're naming them, we have the element and we put a special ending on it, an IDE ending. So, if I am looking at fluorine, I drop the INE and I get fluoride. So, if I talk about fluorine, it's F. It's an atom of that. If I'm talking about fluoride, I'm talking about F1 minus, the fluoride ion. So when you see that IDE, that is telling you that I have the fluoride anion, F1 negative. Now, let's think about another one. Let's talk about oxygen, because you've heard of this guy before. Oxygen. What are you going to call the oxygen anion? Oxide. Okay? Oxide. And the oxygen atom, or the oxide anion, would have a 2 minus charge. Okay? What about iodine? What are you going to call it? Iodide. And what charge is iodide going to have? -1, a 1 minus. Okay? So, you'll get to know those. You'll get to know those. They are on your ion sheet. And let's look at those ion sheets a little bit. I have these right here and here. Let's look at this one first. Let's look at this one first. This is just a list of some common ions. So we have monoatomic cations. Okay? We have monoatomic cations here. We look at the 1 plus charges. We look at the 2 plus charges. Here's some 3 plus. Here are polyatomics. Polyatomics, once again, polyatomic cations are a group of atoms, many atoms, polyatomic. All right? So, these are, you don't see many polyatomic cations. Ammonium is the most common one. We look here, here's some monoatomic anions, as well as some polyatomic anions. And if you flip that over to the back page, I like this guy right here because it helps you associate. It helps you associate some common charges and where they are at on the periodic table. Okay, we said that the alkali metals are all plus ones. Okay, look at the alkaline earth metals. What are they? What are they? Right there, they're plus 2. We talked about the halogens. Okay, so this will help you associate where those are. We'll talk about this bottom part here, this bottom part with the stock system later on, the stock system and the Latin naming. We'll talk about that later on, maybe tomorrow, but it'll be sometime here coming up. This right here is what I call your PAL, polyatomic ion list, your PAL. So if you hear me say, hey, take out PAL, you're going to need PAL. This is PAL. Now this is just a list, okay, that I'm not going to say I did it because Mr. Scott made this list. Mr. Scott created this, and it says up at the top there, this is not a complete list. All right, but once again, just another reference of a bunch of different polyatomic ions. And you're going to see, other than ammonium, the rest of them are polyatomic anions. So these are our ion lists, okay, that are going to help you with your naming of compounds. We talked about that. We're here, we're past this, we're past this, we're past, let's go. Am I going the wrong way? Nope. All right. Binary ionic compounds. Okay. Binary ionic compounds. Binary ionic compounds are simply, binary. Bi is 2. Okay, so a binary ionic compound is a compound that is composed of 2 different elements. The total number of positive charges and negative charges must be equal. Now, we've talked about binary ionic compounds already because we discussed dot notations with certain things. Now, let's relate these. I've got magnesium here, right? I've got magnesium. If you remember, magnesium has 2 valence electrons, correct? Magnesium has 2 valence electrons. Here is chlorine. I look at chlorine. Chlorine has how many valence electrons? How many? 7. All right? So, when magnesium wants to lose electrons, okay, it wants to lose 2 electrons. So, if I give 1 to this chlorine right here, what am I going to need? I'm going to need another chlorine, right? So I'm going to need another Cl with 7 valence electrons so that that other electron can come here. Now, when I do this and I do this, that's where I get my chlorines with the minuses. What's my magnesium going to be? 2 plus. So, if I'm writing out this, what am I going to write out? I'm going to write out MgCl2. Why do I need 2 chlorines? Why do I need 2 chlorines? Because I need my charges to balance out. I know magnesium has 2 electrons to give. Okay, so I'm going to need 2 chlorines. We did, I believe when we talked about this, we talked about calcium chloride when we did the bonding. So do you see how bonding relates to these compounds right now, these binary ionic compounds? We can see that the electron dots, the Lewis structures, okay, how they relate to the naming. So this is magnesium chloride. Now, let's say that I don't have chlorine. Let's say that I have oxygen. What's the charge of oxygen going to be? 2 minus, okay? So would I need 2 oxygens? No. So if I had magnesium oxide, I'm just going to write out MgO. Okay? Note that the charges of the ions are not included in the formula. Okay? The charges of the ions are not included in the formula. I've seen a lot of students over the years want to do this, folks. They want to put the magnesium and have the 2+ in there. Okay? We don't need them. We don't need them because we know how many electrons magnesium wants to get rid of, right? We know how many electrons that chlorine wants to attract. So we don't need to write those into the formulas. Now, the crossing over method of balancing charges. I don't particularly use this method, but I'm going to show it to you. I don't use the crossover method because sometimes the crossover method is not correct. Okay? It's very few, but sometimes it's not. Okay? So, when we are dealing with naming these compounds, or actually writing the formulas from them, here we have aluminum oxide. And something that I haven't stated yet, but right here, this particular line, write the cation first. The cation comes first, the anion is second. Cation is first, the anion is second. So if I'm going to write my cation, what is aluminum? What is its charge? Aluminum is 3+. So if I'm writing aluminum, I write the cation, 3+, and I write the anion, which is oxygen, as a 2-. So what this crossing over method is you see that aluminum is 3+. The crossover method says that I take this 3 and cross it over to the oxygen. I take this 2, cross it over to the aluminum. And if you do so, the charges should balance out. So what would my total charge of aluminum be? Each one is a 3+. How many aluminum do I have? How many aluminum do I have? Down here, folks. I have 2 of them. So what's my total charge of aluminum? 3 times 2 is 6 positive. Here's oxygen. How many oxygens do I have? I have 3 of them. Each one has how much charge? 2. So my total charge is 6. Now, this is the crossover method. I don't like using that, like I said. What I do is I just look at those charges here, and I see a 3, and I see a 2, and I say, okay, what's my lowest common multiple? 6. I take them both to 6s then. So I know that I'm going to need 2 aluminums to get to 6, and I'm going to need 3 oxygens to get to 6. Okay? That's the way I like to do it, but the crossing over method can be beneficial. can be beneficial. There we got the crossovers there. Now, here is why the crossover method is not 100% foolproof. This is why the crossover number or the crossover method is not always foolproof, because I could have crossed them over and have not the smallest whole number ratio. And just the simplest way to show you this is by actually doing one. Let's say that I have lead. Lead can take a 4+ charge. Oxygen. We said oxygen's a 2-. If I cross over, if I use the crossover method for this, I'm going to get Pb2O4, aren't I? Is that the simplest whole number ratio? No, this is not correct, because it's going to be PbO2 is the correct answer right there. Now, if you use my lowest common multiple, what are you going to take both of those to? What's the lowest common multiple of 2 and 4? 4, right? So you say, okay, I need one of those, I need 2 of those. So that's why I use the lowest common multiple and not the crisscross, because the crisscross could be wrong on certain instances. Okay?